All right, thanks, Steve, and thanks to everyone who came. Glad you found the place. I'm based in Houston, Texas, and I have been over in Europe since the middle of last week. So for me, that meant there were several mornings where I woke up early and I was listening to the end of baseball games. Any baseball fans in the audience? Not really? Okay. Well, the Houston Astros just eliminated the New York Yankees, so that was a great event for us from Houston. And it has some relevance for our field because this is a team that has really embraced data and analytics. So they've used analytics techniques to figure out who to sign for their team, and also when the game starts, where each player should stand for each opposing batter to wait for the ball. So they were ridiculed for that for several years while they lost 100 games each year, but the last 3 years they've won over 100 games each year, so now other teams are starting to take a closer look at that. But anyway, I'm here today to talk more directly about things I work with in my profession, developing performance tools for B&C. Because of that, I'm always interested in the instrumentation that DB2 provides to assist in seeing what's happening with your SQL and being able to assess where the biggest needs are for tuning, and also to be able to assess your tuning efforts to see how successful they've been. And recently, the area that I've been focused on is what I'm calling the cached SQL performance statistics. So that's my topic today. So what I hope to cover is give you a good idea of what that is, and then how you can activate those statistics to track your SQL performance. Once you do activate that, what it costs, and then what its value is. So I'll go through some fairly straightforward examples of SQL in need of tuning and how these statistics can highlight that, and then show the benefit of tuning on that SQL, and also cover a few situations where you really need to look at other things to help with your application performance. Feel free to ask questions at any time, and with that, I'll get started. With a little background, you could probably consider accounting traces as the traditional way of capturing application performance in DB2. So this is divided into classes. You've got classes 1, 2, and 3 of accounting that cover your in-application performance, your in-DB2 performance, and your wait times, respectively. I know when I first got into this field, there was some concern on the part of some customers that it was a bit expensive to run those 3 classes all the time. But I'm just curious, for those of you that know, that are here, how many of you run classes 1, 2, and 3 of accounting on a regular basis in production? Okay, a good number of you do that. And then you can also turn on classes 7 and 8. So 1, 2, and 3, for the most part, you can think of as being at the thread level. There are some exceptions to that, where you can roll up multiple thread executions into one accounting record, or you can base your accounting records on the unit of work. But you can kind of think of it for the most part as being at reporting at the thread level, what's happening in your thread. But classes 7 and 8 are at the package level, so you get that added granularity at a little bit more cost. So I'll repeat that question for classes 7 and 8. How many run classes 7 and 8 just on a regular basis in their production environments? Okay, maybe about a third. So as the SQL is executing, it's updating numbers in memory, statistics that eventually will get pushed out as accounting records. So that's when you think about the cost of running that trace. It shows up pretty much as the time that's consumed by the thread, or specifically often by the SQL as it executes. And then typically at the end of thread or at commit time, that's where the record gets pushed out. So back in DB2 version 5, IBM introduced the dynamic statement cache. And that's, at the time, that was not something that the SQL execution really interacted with, except at prepare time. So at prepare time, the cache was very useful in terms of, that second time you prepare the same statement, that information that was determined for the dynamic statement regarding the access path is sitting in the dynamic statement cache, ideally, and then you can pull that in and reuse that information instead of going through the full prepare of invoking the optimizer and determining the best path for your SQL that you're preparing. So that's the dynamic statement cache. There are a number of entries in the cache corresponding to SQL statements. You can control the size of the cache with a zparm. There's some other things you can affect as far as the behavior. There's a bind option where you can tell DB2 to concentrate statements that are identical with the exception of literals. So, select column 1 from table A where column 2 equals B, or select column 1 from table A where column 2 equals Z or Z. You could specify that those be concentrated together as the same entry in cache. There's also, really the dynamic statement cache is part of the EDM pool of the DBM1 address space. Also in the EDM pool, there are entries representing static SQL that are kind of similar, but the difference is all of that access path information is determined at bind time and then is hardened into the DB2 directory and then pulled into the EDM pool at the time that the static SQL executes. So in either case, either with the dynamic cache or with the EDM pool, an entry has a lifespan where it can end, it can be cast out from the cache or the pool, typically because the pool is full and something else needs to come in and it hasn't been referenced for a while, the least recently used kind of situation. Or it can be invalidated in the case of a dynamic entry. If you do a schema change, change your indexing scheme, update the catalog statistics, then those are events that can cause the cache entries to be invalidated and cast out from the cache. So starting with DB2 version 8, DB2 added the ability to track performance statistics in the entries of the dynamic statement cache. So now with SQL executing, it's pushing statistics out to the cache entries that are an accumulation of what's happened for that SQL statement while it's been in the cache. And then that's the SQL execution and the thread itself never push that out. But one way that you can obtain that information is with an explain. So there's a parameter on explain statement cache. And when you run that type of explain, it takes all of the performance information that's in those cache entries and pulls them into an explain table called DSN statement cache table. Then more recently, the same capability was added for static SQL as well. So the entries that are in the EDM pool for static executions are now being updated to reflect what's happened for each execution of that static SQL as long as it stays in the cache. With the static statistics, there's not an explain capability. So the explain only pertains to the dynamic. But with static, you can write a program. You can use the DB2 instrumentation facility interface to issue a read-s to get that information in the form of DB2 trace records. And you can do that for either the static or the dynamic. The other thing you can do is you can start a trace for class 29. And what that says is when any entry gets pushed out of the cache, at that time, to externalize a record and send it to your trace destination. So a few different ways to get at that data. And just to recap what I've described, these are entries representing SQL statements that give you a history of that statement's performance as long as that entry stays in memory, either in the dynamic statement cache or the EDM pool entries. Now, each one of these entries is an explainable statement, something with an access path. So you won't find DDL type activity in there. You would not see entries representing commits or rollbacks, things like set current, package set. So these are statements with the access paths that are being tracked in this cache and that you can get the performance numbers on. And it's useful because those are also the kinds of statements where it can look at things that might influence the access path to improve your performance. And then the time that each entry spends in the cache can vary quite a bit. So you could have a statement that gets executed very frequently at close intervals, close together. That statement would be more likely to stay in the cache for an extended period of time, where if you have a statement that only runs typically once a day or at some very infrequent interval, then that one's more likely to be removed relatively soon after it executes. So when you do an explain or a read-s type operation, you're kind of getting a snapshot of what's currently in the cache, and the entries that you look at, the ages can vary quite a bit. So what's in these records? You have some context, some things that establish what the SQL statement is. You always get the package, and then depending on whether it's a dynamic or static, you could get information about the user, either the auth ID or the SQL ID that was in effect when the statement ran. For static, you get the collection ID. The statement ID is a value that's assigned by DB2 that represents that entry in the cache, for the life of that entry. So that's one ID, but then you can also specify in the application, you can assign a token to that statement that would be more repeatable, that you would see it consistently each time it gets used and pulled into the cache. The SQL text is being maintained, and like when you do the explain and pull it into that explain table, it gets externalized as a large object in that table. But then actually just on the dynamic side, this query hash is a 16-byte value that IBM calculates based on the statement text. So it's kind of a shorthand representation of the text that would repeat each time you were to bring that text into the cache. And then you've got information about when the entry was created, so you can tell from that how old the entry is that you're looking at. So there's a number of timings. As you might expect, there's an accumulation of elapsed time for that statement. Also the CPU time, and that includes both the standard time and the zip time, where if you're looking at accounting data, you've got those reported separately. But here it's all together as one CPU time. And then a number of wait times. It's not quite as granular or detailed as an accounting trace, but you get maybe a dozen or a little bit more than that as far as different categories of wait and how much time it's spending, the statement is spending in those various types of waits. If the statement's accelerated, then you get the accelerator timings that tell you, how long it was actually being processed in the accelerator, and then how long it took for DB2 to process it once the results started coming back. Then you have some counts, how many times the statement ran, how many get pages were issued, and then I/O activity, a lot of the same things that are being counted in the accounting traces. Information about parallel query successes and failures. And then these last, accelerated executions, and then those last three I'm going to talk about on the next slide. But to get all the details of what's included, there's a library called DSN IVPD, and then there's a member in that library called DSNW messages. That member has all the descriptions of every trace that you can start and what each field represents. So that's one source that you can go to see what you can generate with these cached statistics. Also, you can look at the column descriptions for that explain table, DSN statement cache table. So, for the most part, the cached statistics are less detailed than what you get from accounting. But here's a few fields that I saw that I don't really recognize from looking at the accounting data that I thought were fairly interesting. The rows examined and rows processed, those are both numbers that you want to drive down as much as you can to get the best performance. The rows examined is typically related to the index access or the technique that's used to get to the rows to begin with, to start to evaluate them. So typically it's an index use that would drive that count down. And then the rows processed is looking at the number of rows that came out of your stage 1 processing. So in either case, you want to get those as low as you can while still getting the result set that you wanted from the query. So we're also tracking the table space scans and the index scans. So like in an accounting trace, you might expect to see a large number of get pages, and then you would kind of think, well, maybe that means I'm doing a table space scan here. And then maybe you go look at the explain and see, oh, sure enough, it's doing a relational access type. In these statistics, it's explicitly reported. Here's how many times it scanned the table space. Here's how many times it scanned an index. And then same thing with sorts performed. You get a count of whether sort was invoked, how many times it was invoked in the execution of the SQL. So I think of these as giving you real numbers about what actually happened when your SQL was executing that's closely tied to what you would get from an explain. When you're looking at the explain, it's ahead of time. You're looking at the access path and considering what the behavior will be of the access path, and then these statistics give you some validation or kind of show in reality what's happening as far as the behavior of the access path itself. So what does this cost? And comparatively, the different things that you can do to capture SQL performance numbers, what does each one cost? So I ran a test to answer this question, and the workload that I ran to measure this, I have found that it's been helpful to go with very trivial SQL because for me, I found that that's the best way to get a repeatable result. I can run these million trivial select statements and pretty much get the same result each time as far as the CPU consumed. I think there's some details in the notes, but the select statements that I used, they took advantage of some index look-aside, so they did very few get pages, but it just established a baseline that was very consistent, easy to work with as far as progressively adding other techniques and seeing what the impact was of each one. I did mix in a few cursors in addition to the very trivial select statements. And the overall workload, the overall baseline was about 11 seconds of CPU. So then each bar represents how much was added in milliseconds as I ran this workload. So as you might expect, as we increase in granularity, there is some added cost. So the accounting class 1, 2, and 3 for the thread is a number that's less than 5%. And with the baseline being so trivial, the percentage added is going to come out probably higher than it would for a typical real workload. And then for package, you can see when I added classes 7 and 8, it bumped up just a little bit. And then this third bar is what I'm talking about today, the activation of these cached SQL performance numbers to get the performance numbers at that statement level. So definitely an increase there. But then if you compare it to like a performance trace that's been around for quite a while, with a performance trace you can see things at the individual execution level versus the cache statistics are more accumulated for each statement. But a big difference as far as the cost. This fourth bar, I ran a test where I had turned on an ifkid that was associated with retrieval of SQL text. And I was checking to see, by activating that ifkid, whether that caused more work to be done in order to be able to provide the text. And it looks like that was not the case, that that's just an ifkid that you request when you want the text, and it doesn't really affect what happens while the application is running. So some of my slides, I've made reference to the ifkids that are involved here. But just to spell out what you do to activate this, this tracing, you would start a DB2 trace for ifkid 318 to activate the dynamic performance capture, or ifkid 400 to capture the static. And those pretty much just serve as switches. You never really get a record that's back that's got that ifkid number on it. But then once you've activated the collection, as I've described, there's a number of ways that you can pull those statistics to you or have them pushed to you. So there's the explain statement cache, sends it out to an explain table. That's only for dynamic. You can do an all, which means give me everything that I've got authority for. Or you can do it by statement ID. And actually, you can also do it by token, which I didn't list up here. But if you did assign a token to your statements, then you can use the token to retrieve your result as well on the explain statement cache. So that's the explain statement cache. And then, like I said, you could also write a program that does a read-s to pull those numbers in the form of trace records. You would ask for, if it's 316 and 401 in that case. And similar to the explain, you could do some filtering in your program to just get a subset, or you can get everything that you're authorized for. And then, like I mentioned, the ifkid 317 is what you can ask for through the read-s to get your dynamic text for your statements. So also, all of those techniques involve pulling the information in once it's been accumulated in that cache. But if you start one of these class 29 traces, then the information gets pushed to you every time that an entry gets pushed out of cache. It produces a record, and you get it at your trace destination. So with the explain and the read-s, the snapshots where you're pulling the information, there's a limitation on the coverage there in that you could issue, if you issue the explain or the read-s right after an entry has been flushed, then you miss it. You don't get the information for that statement that may have been quite active for a while and accumulated quite a bit of information, but then was just recently flushed from the cache. On the other hand, with the class 29 technique, you do get what was flushed from the cache, but if a statement stays in the cache for a long period, maybe indefinitely, just because it's being executed so often, then you never get that information in your the data that you're pulling with class 29. So it would help if you could combine those techniques. If you want to get a complete picture, it would help to be able to take a periodic snapshot and then take a look at the entries from one snapshot to the next, and then you would know that whatever had changed, whatever the difference was between those snapshots, you can say that's what happened for that statement during that time. And then if a statement wasn't there on your first snapshot and it was there on your second one, then well, everything that you see was during that period of time. And then if a entry gets flushed, you would combine the receiving of the trace records with your snapshots to kind of build a full picture of what happened for each interval. And then you'd have a history that you could refer back to, and you could use that for comparison. If it looks like you're having some problems with your SQL now, you can go back and see what it was doing before based on those periodic snapshots and that history that you've accumulated. So I'm not a Rex programmer as my primary profession, but I did try some things with Rex to see what I could do that was similar to what I just described. So I set up a historical table that looks just like the explain table, but it has one additional column to represent the period, and then one less column where I chose not to repeat the SQL text on each row of the historical table. And then also I did a separate table just to hold the SQL text on a historic basis. So with those tables, I set up a Rex exec to issue the explain statement cache all, and then to pull that information from the explain table, push it out to my historical table after applying the deltas to account for what happened during that period between the snapshots. Rex made it pretty easy to do that. When you work with Rex, you've got a structure defined for what the SQL descriptor looks like, and it was very easy to step through the columns in that descriptor for any numeric column just to do the math to determine what happened during that period, and then push that out as my result in the historical cache table. So I pretty much stopped there as far as what I did in the Rex. So that left some limitations in that it was only for dynamic because I was basing it on the explain. It's set up, to connect to one DB2 subsystem. So across the data sharing group, you'd want to apply this and accumulate things from multiple subsystems. And I didn't include the class 29 information when entries get flushed. So, if I were to just stop and to use that technique, I'd probably want to run the snapshots fairly close together to avoid missing a lot of things that got flushed in between. So, if anyone's interested, you can contact me. I can give you a copy of what I did with the Rex. But I also, as part of the gathering of snapshots, maintained the statement text table that's got a timestamp saying, this is the last time that this text ran, and the query hash that came from the IBM assignment. So you can use that last used column to periodically go through and remove entries from the text table. So how can all this help? So if you just activate this collection and you have it available to you in your explain table in the case of a dynamic, then it helps just to have that visibility to be able to identify what SQL statements are the most expensive. So I have a couple of queries here that are just based on that explain table. The first one's looking at total CPU consumption. And so that in many cases that's important because you want to factor in even if a statement doesn't consume a lot of CPU or resources on one execution. If it's one that's very frequent, then you can still get quite a bit of benefit from making an improvement on that statement's performance just because it runs so often. On the other hand, you do have the limitation with the explain table that these entries can be of varying age, so it's also useful to do queries based on average. So that second one's an example, just looking at CPU average cost. So if I'm building a historical table, like in that example with the Rex exec, I can give priority to totals over averages because I have some history here and kind of a consistent frame of reference in the historical table that I've built. So these are a couple of queries that are just for yesterday, current date -1, and just doing queries on this historical table to identify the SQL that's the most expensive. In the case of the first query, the most expensive by CPU time. Order by sum stat CPU descending. And then the second query is an example of a query where you would just pull out the text based on a query hash that you had from the first query. So as far as reporting things from that Rex exec, I added some input capabilities where you could tell the exec what to look for, what criteria to sort by in the result, and then how many statements to list. So you could do some input that says, give me the top 100 by CPU cost on the statements. So I don't know how many work with Rex a lot in here, but I did find it was really useful to use the interpret capability in Rex. That's kind of a dynamic ability to build a string and then execute that string in the Rex. That was useful because, again, I could go to that SQL descriptor and just step through the columns, and then I could just pull the column name out from that descriptor and the value, and then just build a string that says column name equals value. And then I could just go through a loop to actually assign Rex variables without really having to explicitly spell out the Rex variables, but just to dynamically populate those based on the column names. So there's an advantage there. If columns get added later, I can still just run the same code and not have to update it to reflect the new column names. So once I did that, I could put reports together from the Rex just using column names. So I was able to take the information that was in the explain table, format it out, knowing it was sorted by the order by, then I could generate information about each statement. So this includes some Rex functions to format out the numbers in a particular width, the number of decimal places, and also some simple formatting on the SQL text itself to make it somewhat readable. So with that in mind, I've got some specific examples. These are fairly basic examples of SQL that could be improved through various techniques. And I just wanted to show for each case what you can see, what you can observe in these SQL cache statistics, and then how you can use that to make a change and then view those same statistics again to verify that you've got better behavior and better results in your SQL. What I did, I took the sample database that IBM provides that's got the employee table, department table, project table, and so on. And I extended out the employee table to be 1 million rows. And also denormalized a little bit. I added a department manager name, and that was so that I could show you this first example. So this is an example where the predicate matching on manager name from department and last name from the employee table that causes the employee table to be scanned because there's no index available for last name on that employee table. So what you see in the statistics, I ran it 500 times, and it used between 3 and 4 minutes of CPU for those 500 executions. A lot of, each time I ran, it did a table space scan, and the rows examined, kind of that first level of row access was 500 million because of the million rows in the table. And only 500 rows came out of the stage 1 processing, and that was actually the result set. So it does turn out that I could change that query to take advantage of an existing index, and instead of using manager name, I can use manager number from the department and match that with the employee number that does have an index. And so there's a big difference here. Still 500 executions, but instead of going from 3 to 4 minutes, it's a tenth of a second. We're no longer doing the table space scans, and our rows examined is way down. So a big savings that these statistics will verify, give you that insight into what's happening in the access path, both in the before case and the after case. A similar example for the need to add a new index. So this one is also based on a predicate with employee last name. And you might conclude, if that's out there and being used heavily, that it could make sense to go ahead and add an index based on last name. So at the before case, I ran this for a set period of time in a loop, just repeating it over and over and doing those snapshots. I got 426 executions in, used a little over 3 minutes of CPU, and similar to the previous example, you see a lot of scans happening, a lot of rows being examined to only get a few rows back in your result. So I'll go ahead and create the index on last name for the employee table. And in so doing, it's a similar dramatic reduction. Actually, because I used the same period of time, I went up from 426 to 1,200 executions. But even with that increased number of executions, the CPU is dramatically reduced there. And you eliminate the scans, and you see the corresponding drop in the rows examined. And the rows process is still the same per execution. This next example I took from the Managing DB2 Performance Manual, talking about stage 1 versus stage 2 processing. So this before statement, I guess the query is looking at how many employees would, or identify the employees who would make greater than 50,000 if the salary were to be increased by a parameter marker percentage. And the way the query is structured here, every time a row is retrieved, we have to do this calculation to perform our filtering of the row. So that means we're going past stage 1 into stage 2 processing. So for 500 executions, it was 11 minutes of CPU. We are, doing the scan here, but our rows examined 500 million, and the rows processed 43 million. So that query can be rewritten as described in the manual, such that the salary, the variable portion is on the left side, and then you can put the rest of the expression, or you can put an expression on the right side that only has to be evaluated once before each row is before all the rows are retrieved. And in that case, what shows up as far as access path behavior is that your rows process goes down. So that's reflecting better filtering at the stage 1 level. You went from 43 million to 11 million, and then there's a corresponding drop in CPU, down from 11 minutes to a little less than 4 minutes. So big improvement there, as you can see with the statistics that are being maintained in the cache. This is an example for a parallel query more oriented toward elapsed time. And this is just a scan. So apparently someone is wanting to stay really up to date on what the maximum salary is across all the employees. So when you run this and do the scan without parallel groups, your elapsed time is between 4 and 5 minutes. But if you do activate the parallel query capability, then that does show up in the statistics that now you've collected or you've created 500 parallel groups, and as expected you get the big reduction in your elapsed time to get that result. It is tracking parallel groups created, which means that it gets incremented by 1 every time a group is created, but you're not getting the count of how many tasks are in the group. You do get that with the accounting information, but not with these statistics. Okay, a sort elimination example. So this is a union, and because it's union and not union all, there is a need to eliminate duplicates from the result set. And so that involves invoking sort to get an ordered list and be able to throw out the duplicates. So when you run this query 500,000 times, it uses 24 seconds of CPU. Maybe not too bad, but then in this example, I'm not using the big employee table. This is a couple of those smaller tables from the sample. And I'm invoking sort each time that I run this query. So there could be situations where you know the data, you know that you're not likely to get many duplicates, or if you do get duplicates, that can be fairly easily handled in the application. And if you choose to go that route, you could specify union all instead of union, which then means you're no longer invoking sort. And in this case, you do see an advantage there where you've cut the CPU time by about 1/3 with your the SQL consumption of CPU. So another technique to eliminate sort would be to have a clustering index. If there's a column that you typically order by in your result, then that order by, in this case, order by impno, could be covered by an index, a clustering index on impno, to take advantage of some sequential access of the rows and being able to get back an ordered set without having to invoke sort. But in this case, it's on a disorganized table space. And I kind of went for the extreme example as far as this million-row table where I did a lot of random inserts to see just how bad the performance of the query could get due to the disorganization. And this is really just one execution of that query. Used 7.3 seconds of CPU, but then over 40 seconds of elapsed time with a lot of get pages happening, over 200,000 synchronous IOs. And this is actually I/O wait time, so you can see that it's about 90% of your elapsed time is spent waiting for IOs to complete. So because of the disorganization, you've lost the ability to bring things in sequentially and get good performance on your query. So if we go ahead and organize that table space and run the same query, you can see a big reduction in the CPU, and then even more dramatically on the elapsed time, going from over 40 seconds to under 2 seconds. And big reduction in the get page count and the synchronous IOs that are happening, and almost no wait time, or comparatively because of the better organized data. So you can use these statistics to verify that in this case the reorg did help the performance of your SQL. So I went through multiple examples where these statistics do help. Now there are some scenarios where that would not be covered by these statistics. So I have a few examples of that. Prepare issues. I talked a little bit about the benefit of the dynamic statement cache for prepare. And that applies across the board. Anytime you do a prepare, potentially it can be satisfied from the dynamic statement cache. You can also, when you bind, you can specify keep dynamic yes, which means I don't want to have to prepare again after each commit. And in some cases, that means the next time that the statement runs, because you're not required to do a prepare, that information could also be satisfied from the cache. But it may be that it's not satisfied from the cache, in which case you have to have an implicit prepare taking place. And there are things that is being tracked in the accounting and statistics records, so that's something that you could look at to make sure you're getting a good cache hit rate on your prepares. You can, as you get into DB212, you can also look at a new capability where you run a workload. You capture that workload of dynamic activity, including the access path information. You can actually harden that information out to the catalog such that the dynamic performs a lot more like static the next time that the next time a prepare happens. Then potentially if there's nothing in the cache to satisfy that prepare, it can then go out to the catalog, to the hardened copy, and pull that in so that you don't have to go through the full optimizer access path selection. Regarding prepare, and also I've seen this reported for static executions as well, things can happen in the catalog that cause performance problems. An example would be, I had a customer who said that their table for tracking authority of the user to execute the SQL was cluttered up somewhat, had a lot of extra entries, and was not well organized, and that was actually causing some problems for the prepare and the SQL execution actually. And so that's something that you can look at as far as are there any issues with your catalog. Typically, you're going to have your catalog showing up as buffer pool 0 statistics in your accounting, and hopefully, your application data is in a different buffer pool, so you can see from the accounting information for buffer pool 0 if there's some issues in your catalog that could affect prepare and execution. So your application could be affected in terms of performance and also recoverability due to commit frequency. These in-cache statistics don't really track what's happening as far as your commit activity. So things to look at there would be your package level accounting, where you can see commit counts per package and get an assessment whether you need to consider committing at a different frequency for that. Also, a number of vendor-provided SQL monitors will actually capture how much time is being spent in commit or rollback, so that's another possibility. IDA eligibility. So with these statistics, we are reporting accelerator activity, but there's not really a way to assess something that's not accelerated and to easily see just from those numbers whether it would be a good candidate for acceleration. There is a system parameter called Excel model that you can turn on, and if you turn that on, you do get some numbers added, or you get some fields in the accounting section populated with a projected savings that says, if this statement were accelerated, here's how much time you'd be saving by accelerating the statement. So you can use that to kind of look at your best candidates for acceleration. So I had an example with just one table that was pretty obvious as far as a need for a reorg. You might have some other examples where maybe there's multiple tables, multiple objects involved, and it may not always be clear which one would be the best as far as reorging or have the most impact, would help the most. So for that, you could also look at these buffer pool numbers per buffer pool in the accounting. And if you have some separation between the objects in the buffer pools, that could give you an idea as far as looking at your synchronous I/O counts in the accounting for buffer pools. Also, those vendor monitors for SQL can also typically give you some numbers at the table and index level as well. And variabilities in performance. So everything that you're looking at in these cache statistics is accumulated, so you can look at totals, you can look at averages, but you don't really have a footprint of kind of the spikes that might be occurring. So that may be something that you're kind of blind to if you're relying only on these numbers. There are some things you can do to get that more granular reporting. I mentioned the performance trace before. That was the big bar at the end. That, of course, you wouldn't want to do that in a production environment or do that, kind of across the board. There's also a capability within the application where you can say set current explain mode equals yes. That generates explain information as the statement is being prepared and executing. So it would be a more granular picture of what's happening on the executions going out to your explain tables. But there is a similar consideration there as far as what it would add, the cost of that. So you could probably do that in a testing type of environment, but most likely not. You wouldn't want to invoke that cost beyond that environment. So yeah, there are SQL monitors where you can actually set thresholds and have things trip, get alerted if a threshold is exceeded. So that would be something to consider as far as capturing those spikes and seeing the high water marks. So I've been talking about these cached SQL performance statistics, and I hope this has been helpful for you and something you can use. And feel free if you had any questions to ask. And thanks for your time.